Chromatography is an analytical method that allows us to be able to separate components of a mixture based on physical properties, specifically on the property of polarity. And so what we have in chromatography is in your mixture, you have components that each of them is going to have a slightly different attraction or affinity for one of the two phases in the chromatography procedure. You have a stationary phase, which, as the name says, is going to stay still. And then you have a mobile phase, and again, the name is pretty self-explanatory. That material is going to be traveling, and it will be traveling through or along the stationary phase. The sample is spotted onto or introduced to the stationary phase, and then the mobile phase comes along, and based on the affinities of those component molecules for the molecules in the mobile phase versus the affinity that it has for the stationary phase, you start to get some teasing apart of the different components. So different types of chromatography, three of which you see here. You have thin layer chromatography, also paper chromatography is done in a very similar sort of fashion with a similar setup. The main difference is that in paper chromatography, the stationary phase is paper, whereas in thin layer chromatography, it is usually a very thin piece of glass that is coated with silica gel, kind of a whitish powdery material. Column chromatography would basically be like thin layer chromatography, except instead of flat, it is cylindrical. And so the entire column is packed with the silica gel material, the stationary phase, and your sample would then be poured on top, and as it drains down through, you add solvent to dissolve the sample. And the one thing about column chromatography over thin layer or paper chromatography is you can actually collect each sample as it elutes from the column. And so, that would allow for additional study to be done. Then you have gas chromatography, and as the name indicates, gas is going to be involved. This would be for substances that can be vaporized and put into the gaseous state, and the mobile phase is a gas. So we'll pick that up and carry it through what we call a column, and that column is very similar in concept to what you have in column chromatography. You have your stationary phase packed within that gas, the GC column, and then gases are what push the components through. And again, based on the differences of polarity, those will be teased apart. The way that we can compare one chromatographic run to another is through something called the RF value, or the retention factor value. And what this is a comparison of how far did the solvent, or the mobile phase, travel versus how far the solute, or the component, the mixture component, travel. And so you would take the distance traveled by the solute, known as the solute front, divide that by the distance traveled by the solvent, or the solvent front. And so if you have the same chromatographic system set up, meaning you're using the same solvent, same temperature, same type of stationary phase, then when you reproduce that study or you test another sample, as long as those conditions are the same, then you should have the same RF value across multiple trials and multiple days that you're doing these. And so thereby you can use that for identification purposes. So to calculate the RF, we need to take some measurements. So this would be, a strip representative of the stationary phase in a paper chromatography. Again, if it's TLC plates, probably be squared off on the bottom rather than pointed in this way. And so what would happen is you would, in pencil, mind you, because a lot of pens may be water soluble or soluble in other solvents, and we don't want to lose our origin line, which would be this line right here, and that's where you would spot your sample. And then as you place this in the chamber, the solvent, the mobile phase, is going to begin via capillary action to move upward, and as it passes the sample line, the origin line, it's going to dissolve the mixture in each of its components, And as you now have kind of a battle between the affinity for the mobile phase versus the stationary phase, the different components will be teased apart. And so as that solvent begins to near the top, you would pull it from the developing chamber and mark, again in pencil, mark that distance that it traveled. And then you need to make some measurements. So you want to measure how far did the solvent travel. That would be the solvent front. All right, and so here we get a measurement of 6.05 centimeters. The next thing we need to do is measure the distance that each solute traveled, and if it's a larger spot or a broad spot, generally we go from the middle of the darkest area. So for solute front 1, we'd call that 1.52 centimeters. For solute front 2, we would call that about 4.15 centimeters. So now to calculate the RF value, we need to take the ratio of each of those solute fronts to the solvent front. So the RF for component 1 would be 1.52 centimeters over 6.05 centimeters, and that gives us an RF value of 0.251. For solute component number 2, we plug in the distance that solute 2 traveled, the 4.15 centimeters, divide that by the total distance traveled by the solvent, 6.05 centimeters, and we get 0.686. Notice that it's a unitless value. It's simply a ratio, a comparison. And again, if we were to run the same sample using the same stationary phase and the same mobile phase makeup, these two components should produce results that would give us RF values that are very nearly the same as these.